A logic program is a collection of sentences that define relations, either directly by enumeration or indirectly in the form of logical rules. Here's a simple example. The first 4 sentences here define the parent relation by enumeration. Art is the parent of Bob, and Amy is the parent of Bob. Bob is the parent of Co and Cal. The rule in the middle defines the grandparent relation in terms of the parent relation. X is the grandparent of Z if X is a parent of some person Y, and Y is a parent of Z. So we shall see, given these definitions of parent and grandparent, we can conclude that Art and Amy are both the grandparents of Cal and Co. As previously mentioned, GDL is a logic programming language, in many ways resembles Prolog, the most popular of the logic programming languages. However, there are several important differences. First of all, the semantics of GDL is purely declarative. That is, there's no imperative features such as assert and retract and cut, as in Prolog. Second, GDL has some restrictions that ensure that all pertinent questions are decidable. In particular, all relations can be computed in finite time. And finally, there's some reserved words, which tailor the language to the task of defining games. Despite these restrictions, we frequently use the phrase logic program to refer to a game description in GDL. Logic programs in GDL are built up from 4 disjoint classes of symbols, namely object constants, function constants, relation constants, and variables. In what follows, we write such symbols as strings of letters, digits, and a few non-alphanumeric characters such as underscore. Constants must begin with a lowercase letter or digit. Variables must begin with an uppercase letter. The arity of a function constant or relation constant is the number of arguments that can be associated with the function or relation when writing expressions, as we'll see in the examples to follow. A term is defined as either an object constant, a variable, or a functional term. By functional term here, I mean an expression consisting of an n-ary function constant and n simpler terms. In what follows, we write functional terms in traditional mathematical notation. The function constant first, followed by its arguments, enclosed in parentheses and separated by commas. For example, if f is a unary function constant and g is a binary function constant, if a and b are both object constants, and if x is a variable, then f of a is a functional term, and so is g of xb. An atom is an expression consisting of an n-ary relation constant in n terms. In what follows, we write atoms in traditional mathematical notation just like terms. The relation constant, in this case, followed by its arguments enclosed in parentheses and separated by commas. For example, if p is a binary relation constant, and if a and b are object constants, then p of ab is an atom. A negation is an expression formed using the negation sign, the tilde character, and an atom. For example, not p of ab. A literal is either an atom or a negation. An atom by itself is sometimes called a positive literal, and a negation is sometimes called a negative literal. Finally, we get to rules. A rule is an expression consisting of a distinguished atom called the head and a conjunction of 0 or more literals called the body, separated by the colon-minus operator. The literals in the body are called subgoals. The intended meaning is that an instance of the head is true whenever corresponding instances of all of the positive subgoals are true and all of the negative subgoals are false. A logic program in GDL is a finite collection of atoms and rules of this form. In order to simplify our definitions and analysis, we occasionally talk about infinite sets of rules. While these sets are useful, they're not themselves logic programs. Okay, here are some examples of things that are logic programs. In this first case, we define the parent relation P in terms of father F and mother M. X is the parent of Y if X is a father of Y. X is also a parent of Y if X is a mother of Y. In the second example, we define grandparent in terms of parent, as we saw before. In the third, we define ancestor in terms of parent. Note that the definition in this case is recursive. And finally, we define remote ancestor as any ancestor that is not a parent, using the not symbol. Although every GDL expression is a finite set of atoms and rules, not every finite set of atoms and rules is a GDL description. As mentioned earlier, there are some restrictions to ensure that such descriptions have desirable properties. The first of these restrictions is called safety. A rule in a logic program is safe if and only if every variable that appears in the head or in any negative literal in the body also appears in at least one positive literal in the body. The first rule shown here is safe. Variables x and z appear in the head, and y appears in a negative subgoal. Fortunately, all three of these variables appear in positive subgoals as well, and so the rule is safe. The second is not safe because variable z appears in the head but not in any positive subgoal. And the third rule is not safe because the variable z appears in a negative subgoal but not in a positive subgoal. In GDL, we require that all rules are safe. The next two restrictions in GDL have to do with recursion. The restrictions are best defined using this notion of dependency graphs illustrated here. The dependency graph for a set of rules is a directed graph in which the nodes are the relations mentioned in the heads and bodies of the rules, and there is an arc from a node P to a node Q whenever P occurs with the body of a rule in which Q is in the head. A set of rules is recursive if and only if its dependency graph contains a cycle, as this one does. Now, we say that a recursion in a set of rules is stratified if and only a variable in a subgoal relation occurs in a subgoal with a relation at a lower stratum. The recursion in the first rule shown here is stratified because all of the variables involved in the recursion occur in relations that are not defined in terms of R. The recursion in the second rule is not stratified because the variables involved in the recursion do not appear in other relations. In GDL, we require that all recursions be stratified. Another case is stratified negation. A negation in a set of rules is said to be stratified if and only if there's no recursive cycle in the dependency graph involving a negation. For example, the first rule set shown here is not stratified because there's a cycle involving a negative occurrence of R. By contrast, the second set of rules is stratified. This set is recursive, but there's no negation occurring in a cycle. The only negative occurrence of R occurs in the definition of T, and that's not part of any recursion. In GDL, we also require that all negations be stratified. Okay, now with these three definitions behind us, we can formalize the semantics, in other words, the meaning of GDL expressions. We start with the notion of a Herbrand universe. The Herbrand universe is the set of all ground terms in the language. In the case of a language without function constants, the Herbrand universe is exactly the set of all object constants. In the presence of function constants, we add in the functional terms that can be formed using those function constants. Since nested functional terms are forbidden in GDL, the Herbrand universe is always finite. The Herbrand base for a logic program is the set of all ground atoms that can be formed from the relation constants in the language and the elements of its Herbrand universe. For example, given the language shown here, the Herbrand base consists of 6 atoms, and just 6 atoms: P of A, P of B, Q of AA, Q of AB, Q of BA, and Q of BB. That's it, there are no more. A Herbrand interpretation is an arbitrary subset of the Herbrand base for a program. Intuitively, we can think of the Herbrand interpretation as a listing of the atoms that are true in that interpretation, with the sense that those that are not in the interpretation are considered to be false. Given the Herbrand base we just saw, here are 3 different interpretations. Since there are 6 atoms in the Herbrand base, there are 2 to the 6th, or 64 distinct interpretations. Here we've just listed 3 of them. Okay, now, finally, we say that an interpretation delta satisfies an expression in our language under the following conditions. If phi is a ground atom, delta satisfies it if and only if phi is in delta. It's a member of that set. Delta satisfies not phi if and only if phi is not in delta. Delta satisfies phi1 and phi2, and so forth, if and only if it satisfies every phi. Finally, delta satisfies a rule if and only if it satisfies the head or fails to satisfy the body. Or equivalently, delta satisfies a rule if and only if it satisfies the head whenever it satisfies the body. And finally, we say that delta satisfies a rule with variables, which is the common case, if and only if it satisfies every ground instance, that is, every instance with members of the Herbrand universe substituted for variables. Now, in general, logic programming can have more than one model. Consider the program consisting of P of A, B, and the rule Q of xy if P of xy. This program has one model with just P of AB and Q of AB, and it has another model with P of AB and Q of AB and Q of BA. And it has other models as well. However, it's worth noting that the first model is a subset of the second. And it's clear that P of A and Q of AB must be true in any model of this program, but Q of BA is optional. To eliminate such ambiguities, we usually adopt a minimal model semantics for logic programs. A model D of a program is minimal if and only if no proper subset of D is also a model of that program. One interesting property of our language is that every logic program has a unique minimal model. Also, all models are finite. Okay, that's it for traditional ordinary logic programs. Logic programs like these are often defined as closed in that they fix the meaning of all the relations in their program. In open logic programs, some of the relations, called the inputs, are left undefined, and other relations, usually called the outputs, are defined in terms of these. The same program can be used with different input relations, yielding different output relations in each case. So formally now, we define an open logic program as a logic program together with a partition of the relation constants into these two types, input relations and output relations. Output relations can appear anywhere in the program, but input relations can appear only in the subgoals of rules, not in their heads. The input base for an open logic program is the set of all atoms that can be formed from the base relations of the program and the entities in the program's Herbrand universe. An input model is an arbitrary subset of its input base. The output base for an open logic program is the set of all atoms that can be formed from the output relations of the program and the entities in the program's Herbrand universe. And an output model is some subset of its output base. Given an open logic program P and an input model D, we define the overall model corresponding to D to be the minimal model of P together with D, in other words, P union D. The output model corresponding to D is the intersection of the overall model with the program's output base. In other words, it consists of those sentences in the overall model that mention only the output relations. And finally, we can think of the meaning of an open logic program as a function that maps each input model for the program into the corresponding output model. For example, the simple logic program shown here gives different outputs for different inputs. Given P of A, B, and P of BB, and Q of B, the output is R of AB. Given just P of AB and P of BB without Q of B, the output is R of AB and R of BB both. Okay, now, with those definitions behind us, let's get back to game description. As mentioned in the introduction, we can conceptualize a game as a structured state graph like the one shown here. GDL gives us a way of describing such graphs in compact form. The content of a structured state graph can be expressed in GDL using some reserved game-independent vocabulary. The vocabulary is game-independent, and the same words are used in describing all games. There are 10 game-independent relation constants in GDL, namely the ones listed here. For example, role of A means that A is a role in the game. Base of P, base of proposition, means that P is a proposition in the game. Action of A, input of role and A means that A is an action in the game for role, the specified role. Init of P means that proposition P is true in the initial state. True of P means that the proposition P is true in the current state. Whatever that happens to be, we'll see later. Does of R and A means that the player performs action A in the current state. Again, we'll see how that works out later. Next of P means that the proposition P is true in the next state, the one after the current state. Legal of R and A means that it's legal for role R to play action A in the current state. Goal of R and N means that the player in the current state has utility N. Terminal means that the current state is a terminal state. The game is over. GDL has no game-independent function constants. However, there are 101 game-independent object constants in GDL, namely the base 10 representations of the integers from 0 through 100 inclusive. 0, 1, 2, 3, 4, and so forth, up to 100. These are included mostly as utility values for game states, with 0 being low and 100 being high. The first step in writing a game description is to select some game-specific vocabulary to capture the structure of states and actions. For example, here we have object constants white and black as names for the two roles of a game. We use A, B, and C to refer to primitive entities in the game. We have names P and Q for relationships among primitive entities, and we have F and G as operations that can be performed on these primitive entities. Finally, we have some helper relations, R and S. The propositions comprising states can be thought of as either object constants or functional terms in our language formed using the relationship functions. Similarly, actions can be either object constants or functional terms formed using action functions. For example, supplying relationships functions P and Q to primitive objects, applying them to primitive objects A, B, and C, we end up with propositions like P of A and Q of B, C. And applying operations F and G to these objects, we end up with actions like F of A and G of B, C, and so forth. The rules in a game description say which propositions are true and which actions are performed, as shown in what follows, and specify the results of the performing those actions. Finally, we define a game description as an open logic programming using GDL's game-independent vocabulary, together with the game's game-specific vocabulary, subject to a few restrictions here. True and does are input relations to the program. A GDL game description must give complete definitions for role, action, base, and input. And init. It must define legal and goal in terms of an input relation true. It must define next in terms of input true and does. Since does and true are treated as inputs, there must not be any rules with either of those relations in the head. Okay, well, wow, that's a lot to digest. In the abstract, these concepts are difficult to master, and as presented, they're not particularly well motivated. In practice, things are a lot simpler. In the next couple of segments, we illustrate these notions by looking at a specific game description and see how it's used in simulating a game.